This presentation is about the protection systems of electrical power systems. We will discuss two portions of protection systems, the line protection and transformer protection. The main function of line protection system to identify the location of faults and isolate only the faulted section. The key challenge to the transmission line protection lies in reliably detecting and isolating faults compromising the security of the system. The most basic part of line protection is lightning protection. Poles are high in the air and are prone to lightning strikes. A flashover damages insulation and causes a permanent ground fault. Two methods are used to avoid this: a sky wire and a lightning arrestor. The sky wire or static wire is the utmost top line of the utility pole. This wire bleeds off lightning surges from power lines when lightning strikes during a thunderstorm. The static wire is connected to the grounding conductor. But is this protection adequate? The problem with lightning is that sometimes lightning spikes can travel back from the ground. This is why lightning arresters are used to block these currents. However, it is more costly than the sky wire system. Hence, they are used where sensitive equipment is present and must be protected against back currents. What are faults? A path for the flow of current other than the load is called fault. There are two types of faults: ground fault and phase fault. When the path is between line and ground, it is said to be a ground fault. When the fault is between two lines, it is called a phase fault. Faults can be categorized as temporary faults, permanent faults, and major faults depending on the magnitude and time taken to repair them. A transient fault is a fault that is no longer present if power is disconnected for a short time. Many faults in overhead power lines are transient in nature. At the occurrence of a fault, power system protection operates to isolate area of the fault. A transient fault will then clear and the power line can be returned to service. Typical examples of transient faults include momentary tree contact, bird or any other animal contact, lightning strike, conductor clash. Now, how do we deal with this temporary fault? We can use a circuit breaker, but the disadvantage of a circuit breaker is that it has to be manually closed. If such a fault occurs at a remote area, it will take a long time to restore power. As such faults are quite frequent, a better solution is the auto recloser. In a power distribution system, a recloser or auto recloser is a circuit breaker equipped with a mechanism that can automatically close the breaker after it has been opened due to a fault. Reclosers are used on overhead distribution systems to detect and interrupt transient faults. Since many of these transient faults clear themselves, a recloser improves service continuity by automatically restoring power to the line after this transient fault. In case of a more permanent fault, we need to isolate the fault zone completely till the fault has been cleared. Devices like circuit breakers, sectionalizers, and fuses are used for this purpose. But different lines contain different amounts of power. For a fault at a point lower in the power system hierarchy, only that local portion should be isolated. Remaining power system should keep on operating normally. Hence, there is a scope for a sophisticated power protection system which can cater for such requirements. Non-unit type protection schemes take into account these requirements. They have no fixed boundaries of protection and take into account a larger portion of power system. They can even overlap with other protection systems and are compatible with backup systems. These include time-graded protection system, current-graded protection system, impedance-graded protection system. We will explain these one by one. Beginning with time-graded protection system. This system incorporates circuit breakers with a delayed operation. The delay increases as we go up in the power system hierarchy. As we want the circuit breakers near the fault to operate first and isolate that portion without affecting the other system, so they operate more quickly than the other circuit breakers which are closer to the power supply. Similarly, current graded protection system incorporates circuit breakers with a power rating inversely proportional to the distance from the generating station, as the power in the lines is more near the supply. The third scheme is impedance graded scheme. This system incorporates the impedance sensitive circuit breakers. These circuit breakers measure impedance looking into the line and trip if the impedance is too small. The farthest relay is the most sensitive. They also trip if a slight negative impedance is seen for backcurrent protection. Now we will talk about our second topic of interest, that is transformer protection. The transformers used in the system have a rating of 3 kVA to 500 MVA, and they can be 3-phase or can be 3 single-phase transformers connected as 3-phase transformer banks. These transformers are connected in delta or Y connection schemes according to the required voltage or current levels. Y-delta transformers have a phase difference of 30 degrees according to IEEE standards. The degree of protection employed for a particular transformer depends upon its size, its importance in the system, and the economy of the design. For instance, sometimes we don't use the circuit breakers to make the design less expensive. However, appropriate amendment must be made to the design for protection. The transformers are prone to two types of fault: internal faults that occur within the transformer proximity and through faults that occur external to the transformer. Both these faults may cause a very large current to flow in the circuit, which may damage the insulation and hence damage our system. Faults that occur inside the transformer, called internal faults, may be caused by insulation failures like 3-phase shorting, phase-to-ground shorting, phase-to-phase shorting. The internal faults can be dealt with using differential protective relays. Differential protection is a unit type protection for a specified zone or piece of equipment, in our case transformer. It is used only in the case of internal faults. It trips when the difference between the input current and output current is high. There are a few facts to consider for differential protection: inrush current, current transformer connections, phase shift in Y-delta transformer, selection of CT taps, and effect of transformer taps. Magnetizing inrush current in transformers results from any abrupt change of the magnetizing voltage. Although usually considered as a result of energizing a transformer, the magnetizing inrush may also be caused by the occurrence of an external fault. The CTs connected must cater for the phase shift between Y to delta transformers, so they are connected opposite to the configuration of the transformers. For example, if you have a Y delta transformer, then the CT will be connected delta to Y. Through fault withstanding capability has been divided by the IEEE standard into 4 categories as indicated in the table below. Through fault withstanding capability is actually represented in terms of a curve plotted between multiples of nominal current and the allowable time. In this particular example, we have a transformer that feeds 3 feeders through a bus bar. If a fault occurs in any of the feeders, then the respective protective system of a feeder called downstream operates. If it fails to operate, then the high voltage fuse on the primary end of a transformer works. As the HV fuse cannot sense small faults, so we have to employ a backup relay like our 51G relay. This graph depicts the previous example. From this graph, it can be seen that the downstream protection operates before the fuse, and if both of them fail, then our system might be damaged.